政府は電力需給が厳しいとして今日も東京電力の管内を対象にした電力需給逼迫警報を継続すると発表しました。
今晩停電という可能性は回避できるめどが立ちました。
電力の需給が逼迫した東京電力や東北電力の管内では昨日大規模な停電が危惧されましたが、暖房の使用を控えるなどの節電の協力によって回避することができました。しかし政府は電力需給逼迫警報について東京電力の管内では電力需給が厳しいとして今日も継続します。一方、東北電力の管内は電力需要に対する供給余力が 3% を上回る見通しとなり、昨日夜警報を解除しました。ただ電力を供給する余力は大きくないため節電の要請は続きます。
Hi gang, I'd previously demonstrated generating power using atmospheric electricity. A hexacopter was used to lift one end of a wire high up into the air. Meanwhile, the other end of the wire was connected to a CoronaMotor near the ground. Electricity then flowed through the wire and CoronaMotor, making it turn. In this video, I'm going to explain how it works. Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures. To take advantage of this atmospheric electricity, we electrically connect one end of a wire to the ground and lift the other end up into the air. In our case, we got good results at around 120 meters or 390 feet up. At 100 volts per meter or 100 volts per yard, that's 12,000 volts between that height and the ground. But just as with you standing on the ground, the wire is an electrical conductor and so is also at ground potential. Looking at the equipotential lines around the wire, that voltage of 12,000 volts exists between some distance away from the wire and the wire. You can see that the equipotential lines are closest together at the top of the wire. This means the attraction is strongest there, and electrons make their way upward in the wire. Let's look more closely at the top of the wire. We'd put 6 sharp points using sewing pins at the top of that wire, but for ease of illustration I'll draw just one. Notice that because of the sharp shape at the point, the charges are crowded together at that point. Remember also that there are positively charged ions in the air. An electric field exists between the negative charges on the wire and the positive charges in the air. And we can represent that electric field by drawing lines between pairs of opposite charges. Notice that the electric field lines are closer together near the point, meaning the electric field is stronger there. It's strong enough to remove the negative electrons from the sharp point, where they neutralize positive ions. But due to the voltage, there are fresh positive ions moving downward and fresh negative charges coming up from the wire. We now have electricity flowing through the wire. The electric current in that electricity is very weak though. We didn't measure it, but from my experience with electrostatics, I'd estimate it in the low microamps, or more likely even lower. That's not enough to turn an electromagnetic motor, one like you use in everyday life, but it is enough to turn an electrostatic motor, like this CoronaMotor. The CoronaMotor consists of a plastic cylinder surrounded by sharp-edged metal blades. Every second one of those blades is connected to the wire going up into the sky. That means that when the wire starts conducting, those blades are now at whatever voltage the top of the wire is up in the sky, though opposite in polarity, positive. That's why you get a shock when you touch one of those wires. Negative charge is then pulled from the plastic cylinder through a gap between the edge of the blade and the cylinder. That leaves the cylinder with the same charge, and since like charges repel, a repulsion occurs that rotates the cylinder. The next blade is connected to earth ground and becomes negatively charged, and since opposite charges attract, it attracts the charged area of the cylinder. It then neutralizes that charged area by taking electrons from the ground. And that's how atmospheric electricity can power an electrostatic motor like a CoronaMotor. Well, thanks for watching. See my YouTube channel for more interesting videos like this. That includes one with a more detailed demonstration of this atmospheric electricity in action powering the CoronaMotor, another showing how this CoronaMotor was made, and one showing how to generate electricity using a Peltier module. And don't forget to subscribe if you like these videos, or give a thumbs up, share with your social media, or leave a question or comment below. See you in a bit.